Welcome to this comprehensive lecture on the morphological matrix technique, a powerful, systematic approach to innovation and concept generation. The morphological matrix is like building inventions from a menu. Instead of guessing randomly, we systematically explore all possible combinations of design parameters. Let's start by understanding what a morphological matrix actually is and why it matters for innovation. A morphological matrix is a structured framework that helps engineers and designers systematically generate new concepts by exploring all possible combinations of parameters. The matrix lists key parameters as rows, such as geometry, actuation, material, and control. Each parameter has multiple options listed in columns. By systematically combining different options from each parameter, we can create a vast number of novel designs that we might never have thought of randomly. Here's the basic structures of a morphological matrix. Parameters are listed in the left column, and for each parameter, we list multiple options across the row. Let's examine the four fundamental parameters that define most engineered systems. Geometry defines the shape and spatial arrangement of components. Options might include cylindrical, rectangular, spherical, or spiral configurations. These are examples of different geometric options: cylindrical, rectangular, triangular, and spiral shapes. Each offers different advantages for fluid flow, structural integrity, or manufacturing. Material parameters include options like metal, polymer, ceramic, or composite. Each material brings different mechanical, thermal, and chemical properties. Actuation defines how the system moves or operates. Options include pneumatic, hydraulic, electric, magnetic, or thermal actuation mechanisms. Control parameters specify how the system is regulated. Options range from open-loop manual control to closed-loop feedback systems with sensors and adaptive algorithms. Now let's explore the mathematical power of the morphological matrix. How many unique designs can we generate? The fundamental multiplication principle tells us that if we have multiple independent choices, the total number of combinations equals the product of all options. Mathematically, the total number of designs equals n1 times n2 times n3 and so on, where each n represents the number of options for that parameter. Let's consider a concrete example. Suppose we have 4 parameters, and each parameter has exactly 3 options to choose from. The total number of unique designs equals 3 times 3 times 3 times 3, which is 3 to the 4th power, giving us 81 distinct design concepts. Visually, we multiply 3 options for geometry, times 3 for material, times 3 for actuation, times 3 for control, yielding 81 total design combinations. Real morphological matrices often have many more options per parameter, leading to explosive design spaces. Let's scale up. Consider a more realistic scenario with 5 parameters, each having 4 distinct options. Now we have 4 to the 5th power, which equals 1024 distinct design concepts. The design space expands rapidly. If we have 6 parameters with 5 options each, the number jumps to 5 to the 6th power, which is over 15,000 design concepts. Precisely, 5 to the 6th power equals 15,625 unique combinations. This explosive growth illustrates the power of systematic exploration. This bar chart shows exponential growth in the design space as we increase parameters and options. The combinatorial explosion creates vast exploration opportunities. Now let's address a critical question. Why does random recombination of ideas often fail to produce useful innovations? Consider this question carefully. If we have so many possible combinations, why doesn't randomly mixing design elements produce good results? The answer is that most random combinations violate fundamental physical, economic, or functional constraints. They simply don't work in practice. Mathematically, the number of feasible designs is much smaller than the total number of mathematical combinations. Most combinations are physically impossible or economically impractical. This Venn diagram shows the reality. The tiny yellow circle represents feasible designs, while the large blue circle shows all possible combinations. Random attempts, shown as red dots, usually miss the feasible region. Random search wastes enormous resources testing infeasible combinations, Most random attempts fall outside the feasible design space, yielding no useful information. Structured recombination, as provided by morphological matrices, solves this problem through systematic constraint-aware exploration. The structured morphological approach incorporates domain knowledge and constraints up front when selecting parameter options. Only viable options are included in the matrix. By carefully choosing which options to include for each parameter, we pre-filter infeasible combinations before we even start exploring the design space. Efficiency equals the number of feasible designs explored, divided by total resources expended. Structured recombination dramatically improves this ratio. Compare success rates. Random search might achieve only 5% feasible designs, while a well-structured morphological matrix can achieve 60% or higher success rates. Let's work through a concrete numerical example from microfluidics, designing a microscale valve for lab-on-a-chip applications. Our goal is to design a microfluidic valve that can precisely control fluid flow in channels only micrometers wide. We identify 4 key parameters and carefully enumerate viable options for each based on microfluidic constraints. Here is our microfluidic valve matrix. Geometry has 4 options: membrane, cantilever, rotary, and gate. Actuation has 3 options: pneumatic, thermal, and magnetic. Material has 5 options, and control has 2 options. The total design space contains 4 times 3 times 5 times 2, which equals 120 distinct valve design concepts to explore. Each of these 120 combinations represents a concrete, testable prototype that could be fabricated and evaluated in the laboratory. Let's examine the specific options for each parameter in our microfluidic valve example. For geometry, we have membrane valves with flexible sheets, cantilever valves with beam structures, rotary valves with spinning elements, and gate valves with sliding barriers. For actuation, pneumatic uses air pressure, thermal uses temperature-induced expansion, and magnetic uses electromagnetic fields to move valve components. Materials include PDMS elastomer for flexibility, silicon for precision, glass for optical transparency, rigid polymers for structure, and hydrogels for biocompatibility. Control can be simple open-loop timed actuation or sophisticated closed-loop feedback using flow sensors and adaptive algorithms. These simplified diagrams show the 4 geometry options: circular membrane, horizontal cantilever beam, rotary arc, and vertical sliding gate. Now let's explore a real case study from product design: developing an optimized robotic gripper using morphological analysis. The challenge was to design a single gripper mechanism capable of handling both delicate objects like eggs and heavy objects like metal parts. The traditional approach would create 2 separate gripper designs, one soft gripper for delicate items and one rigid gripper for heavy items. However, the morphological matrix exploration revealed a non-intuitive hybrid solution that could handle both requirements. The matrix had 3 options for finger count, 4 material choices, and 3 actuation methods, totaling 36 combinations. One unexpected combination emerged as optimal. This gave us 36 distinct gripper concepts to evaluate through simulation and prototype testing. The winning design used 3 fingers with a hybrid material combining rigid core and soft outer layer, actuated pneumatically for variable force control. This non-intuitive combination would likely have been missed by random brainstorming or trial-and-error approaches. The systematic matrix exploration found it. Another compelling case study comes from microfluidics, designing an efficient microscale fluid mixer. The design goal was to thoroughly mix 2 fluids flowing through a microchannel in less than 1 second of residence time. The initial design space included 5 parameters with 4 options each, creating over 1,000 possible mixer configurations. With 4 options for each of 5 parameters, we had 24 distinct mixer designs to consider. Testing all would be impractical. By applying physical constraints like Reynolds number limits, fabrication capabilities, and pressure drop requirements, we filtered down to 200 viable designs. The funnel shows progressive filtering, from 1024 mathematical combinations down to 200 viable designs, then to top 5 candidates through simulation and optimization. Computational fluid dynamic simulation and limited physical testing identified the top 5 candidates with best mixing performance. The winning design combined a herringbone channel pattern with active pressure modulation, achieving complete mixing in just 0.6 seconds. The morphological matrix is like ordering from a restaurant menu, a helpful analogy for understanding this systematic approach. Think of a restaurant menu organized by categories: appetizer, main course, side dish, dessert, and beverage. Each category lists several options. The menu structure mirrors the morphological matrix. Categories are parameters, and items within each category are the design options we can choose from. To create a complete meal, you pick exactly one item from each category. This systematic selection generates countless unique meal combinations. With 4 appetizers, 5 mains, 3 sides, and 4 desserts, you can create 240 distinct meal combinations by systematically choosing one from each category. Similarly, in design, you pick one option from each parameter row in the morphological matrix to create a complete system design. This systematic selection ensures comprehensive exploration of the design space without randomly guessing or missing viable combinations. Advanced morphological analysis includes a constraint compatibility matrix to identify which option combinations are physically feasible. A critical insight is that not all parameter combinations are physically, economically, or functionally compatible with each other. A compatibility matrix explicitly marks which pairs of options from different parameters can work together in a real system. This compatibility matrix uses green dots for compatible option pairs and red dots for incompatible ones. This eliminates infeasible combinations before detailed analysis. The number of feasible designs equals the total mathematical combinations, minus those eliminated by incompatibility constraints. For example, pneumatic actuation requiring flexible membranes is incompatible with rigid metal construction, so those combinations are marked infeasible. To fix the error, we should ensure that all parentheses are properly closed.